All right, we're about to tackle a huge, and I mean huge, challenge. How do we manage these vast, hidden reservoirs of fresh water that are literally right beneath our feet? Let's get started.
No, really, think about it. Most of our planet's usable fresh water isn't in lakes or rivers, it's underground in these things called aquifers. So if you can't see it, how do you have any idea how much is down there, where it's moving, or if we're using it up way too fast? To answer any of that, we first have to find a way to see it.
And that's where this comes in. We build a groundwater model. Honestly, the best way to picture it is as a digital twin of an aquifer. It's a super complex computer simulation that basically gives us X-ray vision. It lets us see what's happening underground, understand the present, and even predict what's coming next for our water supply.
So how do you even build one of these digital twins? Well, the first step is all about creating a conceptual blueprint. It's about translating the messy, complex real world into a structured digital grid that a computer can actually understand.
And this really shows just how far we've come. The old way, what we call the grid approach, was just painfully tedious. You'd have to manually assign properties to thousands of individual cells. The modern conceptual model approach, though, completely flips that on its head. You start by defining real-world features, rivers, wells, and the software intelligently builds the grid around them. It's way faster, more flexible, and just a much better way to do it. The whole process is actually a pretty logical flow. First, you start with real GIS data, a map. Then you digitize those physical things you see on the map. So a well becomes a point, a river becomes a line, and the whole aquifer boundary becomes a polygon. And then the software just works its magic, laying a grid over the top of all that and translating all that real-world information into its numerical language.
Okay, so now we've built our digital twin. But is it any good? Is it accurate? Because really, a model is just a guess until you check it against reality. This next step, what we call calibration, is where the real work and the real science truly happens.
This quote from a seasoned modeler just says it all. Your first attempt, it is basically guaranteed to be wrong. And that's okay. That's expected, actually. That first model is just a starting point. The real work is in all the refinement that comes after. So that refinement process is called calibration, and it's a lot like tuning an instrument. We just keep adjusting the model's inputs, things like how easily water can move through the soil or how much rain is actually seeping into the ground, and we run it again and again and again until the model's outputs perfectly match what we're actually observing out in the field.
So what are we actually comparing here? It's mainly two things. First, we take the model's predicted water levels, we call these heads, and we check them against the actual water levels measured in monitoring wells. Then, we look at the model's calculated water exchange with streams and compare that to real-world measurements of how much a stream is gaining or losing water between 2 points.
But this is where things get really tricky. What if you have different settings in your model, but they produce the exact same result? This is a huge problem called non-uniqueness. And it's dangerous because it can give you a model that looks right, but is actually right for all the wrong reasons. So here's the big insight. Just matching those water levels or heads is not enough. You can have a situation, for example, where low conductivity and low recharge give you the exact same water levels as high conductivity and high recharge. So the model would look perfectly calibrated, but its internal logic would be completely broken, making it useless for predicting anything. The solution? You have to include streamflow observations. That data pins down the total water budget. It forces the model to find that single, more unique combination of parameters that actually reflects reality.
Now, manually tweaking and rerunning a model hundreds of times sounds exhausting, doesn't it? Well, it is, which is exactly why we now use some pretty powerful software to automate the whole tuning process.
I mean, think about it. With all these different parameters to adjust, finding the perfect fit by hand would be incredibly slow and difficult. It's just not practical. There has to be a better way. And there is. And that better way is a utility called PEST, which stands for Parameter Estimation. You can think of it like an automated detective. It literally takes control of the model, runs it thousands of times, and systematically finds the input values that create the absolute best match with the field data we've collected.
But here's the thing. We can't just let PEST change thousands of cells individually. That's just too complex. So we simplify the problem for it through something called parameterization. A common way to do this is by grouping cells into zones with similar properties.
So here's how it works. First, we identify the key parameters to adjust, like defining zones of hydraulic conductivity. Second, we have to set some boundaries, giving PEST a valid range for each of those parameters. Third,
We just let PEST do its thing. The software runs all these simulations, intelligently tweaking the parameters. And finally, it provides us with the optimal parameter values, which we then import right back into the model.
So we've gone through this whole pretty technical process, but why does it all matter? Well, it matters because this digital model is the foundation we need to make critical, real-world decisions about our water.
A calibrated model lets us ask those huge what-if questions, like how will a new well affect the aquifer and the people who rely on it? Is the way we're using water right now sustainable for the next 50 years? If contamination happens, where will it go? Or how would a really severe drought impact our water supply? These are the kinds of questions a model can help us answer.
So at the end of the day, a calibrated model isn't just some academic exercise. It's a critical tool. It's how we manage our most vital hidden resource and how we plan for a sustainable water future.
What this all means is that our digital view of the underground is clearer than it has ever been. So the question that leaves us with is, what should we be looking for next?